Good afternoon, everyone, and welcome to Burns Engineering's RTDology, our online training series. I'm Jeff Wiggin, National Sales Manager at Burns, and presenting today will be Bill Berquist, Principal Application Engineer. Today's presentation, Troubleshooting RTDs and Thermocouples, is part of our series of web-based training modules designed to help you better understand temperature and achieve your measurement goals. If you've joined us for any of our previous sessions, we'd like to welcome you back. If this is your first time with us, welcome. And when you get a chance, do check out our previous presentations on our RTDology channel on YouTube. Before we get started, just a few housekeeping items. To respect everyone's time, we'll make every effort to limit the presentation and Q&A period to 1 hour. We do highly encourage questions, so please type them into the Q&A section or the chat box on your screen and send them to host and presenter. We'll attempt to answer as many as time allows. The session is being recorded, and we will provide a link to the YouTube recording just as soon as it's available. If we don't get to your questions or you need some additional assistance, there will be contact information provided at the end of the presentation. And finally, our goal is to answer your temperature measurement questions and challenges. We put together our RTDology series based on the most commonly asked questions and issues, but if you have a particular topic you'd like to have considered, please give us a call and we'll see what we can put together for you. So that covers the housekeeping. So without further delay, here is Bill Berquist to provide some background and assistance with troubleshooting RTDs and thermocouples.
All right, well, today what we're going to do is run through, and I've got this session separated into two separate parts. First, we're going to talk about RTDs, and then we'll look at how they're put together, and it helps to understand that so that it makes the troubleshooting make a little more sense. Same thing with thermocouples. We'll start out the same way with a review of how they're constructed, and then go through a troubleshooting guide that I put together, and then talk about some other things that can affect reliability and accuracy of those temperature measurements.
And before we get jump into it, we're just going to have a quick little poll. On the previous screen, you saw a little bit about Bill and I, and we would like to find out a little bit more about who's on the presentation here. So you'll see a poll pop up, and you get a couple minutes to complete that. So if you can, at your leisure, go ahead and just tell us a little bit about the industry you represent and kind of your level of knowledge on RTDs and thermocouples, and we'll take a look at that poll as soon as it's done. All right, looks like we still have a few people working on it. So far, from our end, it's looking like there's a pretty good cross section of folks. A lot of biotech, pharma, and chemical, petroleum. So we'll leave the poll open here for another couple seconds, and then we'll show everybody the results. Okay, I think we'll go ahead and close the poll out now. Appreciate you sticking with us here, and it'll take a couple seconds to compile the information, and then we'll show it so everybody else can see who all we have on the presentation today. Okay, and as you, there we go. And so as you can see, it looks like we've got the, let's see, where are the majority of folks? I have to scroll back here a little bit. So it looks like majority are biotech, pharma, close second in chemical and petroleum. So we want to welcome everybody. And for those of you who did check other, if you wouldn't mind in the Q&A section or the comment section, go ahead and just put in what industry you're with. That would be helpful for us. We appreciate that. And it looks like we've got quite a few people in the in-between stage as far as knowledge. So quite a few sophomores and a few juniors, and we've got some seniors out there as well. So that's a great cross section of folks. So appreciate that. So with that, Bill, why don't you continue?
All right, thanks, Jeff. Interesting stuff there. Good to know. Maybe we can have some of those senior skilled level people answer a few questions if I get stumped here. So we'll just dive into this and we'll start talking about RTD construction first here. The sensing elements in RTDs, there's a couple different types. There's thin film and then there's this wire wound type. And most of the wire wound types are of this construction where we have a coil of platinum wire. It's mounted inside of a ceramic tube. This happens to show a dual element, so there's actually two separate sensing elements in here. Wires really fine diameter, and most of these sensors are very small. 16th inch diameter is very common, and the sensitive length is about 1 inch. The thin film, this is the other style of sensing element. This uses just a thin film of platinum deposited on a ceramic substrate, and you can see here the little traces of platinum. And then that area is covered with this glass material which helps hold the external lead wires in place. And these can be, this is a pretty typical size, about 80 thousandths by 175. 35 thousandths thickness. There are smaller ones and there are larger ones, but this is kind of an average size thin film sensing element. As you can see, if this can be a lot more durable than the wire wound version, because you've this platinum film on the substrate really isn't going to go anywhere with vibration or shock or anything, so these can be very rugged. These sensing elements are packaged two basic ways. We have a mineral insulated sheath where the lead wires are inside of a usually a stainless steel tube, and they're suspended in compressed ceramic powder, either magnesium oxide or aluminum oxide, or some sort of ceramic material that supports those leads. The other style is what we call tube and wire. So you just have the stainless steel tube with some insulated lead wires running down to the sensing element, and they may or may not be supported with any kind of potting material inside that sheath. External leads, most common is copper with either a nickel or a silver plating on them. Nickel's a little better for high temperature applications. Silver is probably the more commonly available off-the-shelf type plating for the copper wires. The plating is necessary because copper will corrode quite quickly inside the probe sheath at the temperatures that these are typically used at. So they need to have some kind of a plating on those copper wires. And then the probe is sealed up where these wires exit, typically with some sort of epoxy. There's several different types that are used. The most common that you probably see is either a black material, and I've seen some that have like a clear epoxy. Either one works fairly well.
Okay, before we get started, we kind of wanted to find out a little bit more what types of failures you folks have experienced with RTDs. So we're going to have another quick poll here that we'll go ahead and get started. And I have about a minute to complete it. So go ahead and you can just tell us a little bit about what kind of failures you guys are running into, so that we want to be sure to address those in this presentation. All right, we get quite a few people chiming in, so that's fantastic. So we got another few seconds here. We'll go ahead and get that done, and then we'll close the poll out and go ahead and show you what the results are. Looks like we got a top 3, so that's pretty good. And so far, everybody knows exactly what the issue is, so that's good as well. So we will go ahead and show the results here. Okay, so it looks like the majority, we're looking at indicating higher or lower temperature than expected. It's pretty common. And we get some erratic output and the dreaded open circuit, although sometimes that's a little easier to fix because you know exactly what's going on. But thanks a lot. And with that, Bill, go ahead and continue.
All right, good. Well, those are actually three of the areas we're going to be talking about quite a bit here. So let's dive into this. And I put together this little kind of little troubleshooting guide. And of course, the first one on the list is the erratic output. This is one of the more common questions that I get. And there's a couple of the main reasons for this is that either the sensor got damaged, and this would be typically like one of those little platinum coil wires, or a lead wire is just partially broken, and as the probe is vibrating, it's making contact at that breakage point. It's not quite completely broken, but it's almost broken, and so you're going to get some erratic output there. The only solution for that is to go ahead and replace the probe. There typically is no repair to an RTD. Second cause of this would be radio frequency or electromagnetic interference. Could be there's a big electric motor nearby. Some of these variable frequency drives, even communications radios if those are used in the facility. And this is something that you can fix. Now this would be making sure that the cable that leads from the sensor to the controller is shielded, making sure that the wiring and everything is routed away from any kind of a noise source. And then if the connection head on the part happens to be polypropylene or some non-metallic, sometimes adding a metal connection head to further shield the terminal block and the wires where they connect to your facility wiring, that can help prevent some of this RFI or EMI interference. Now, if we're getting absolutely no signal, we've got an open circuit situation. Again, you just need to replace the probe. There is really no fix to it. We have run across some wiring deficiencies where it wasn't quite clear to whoever was hooking it up where all the different wires go. There are some different color code combinations that you'll see out there. The two RTD standards specify the colors that you see here. So we've got for a single 3-wire, we've got 2 reds and a white. If it's a 4-wire circuit, there'll be 2 reds and 2 whites, one on each side of that sensing element right here. And then the dual elements, this is where some of the color codes change a little bit. So the standards say one sensor is red and white, the other is yellow and black. Now, there are, in fact, just yesterday I saw one manufacturer had, I think it was red and white and then blue and green. And sometimes I see where the yellow leads are substituted with green, so that's going to be another real common color code. So unfortunately, there's no good hard and fast rule on wire colors. And if there's question, you can either do a quick test with an ohm meter to see which pair of leads are connected to one side of the sensor. So for example, on a single 3-wire probe, this red loop, you're going to get a real low resistance. And if you hit the white lead in one of the reds with your ohm meter, you're going to get about 109 ohms at room temperature. So that's one way you can test, or go back and look at the manufacturer's documentation. Let's see here. The last thing on the list here would be if you've noticed a step change in the output. So let's say you started up your process and the temperature's at 50 degrees C, and all of a sudden you see it it change a little bit. It could be that it steps up in temperature just a little bit, and typically that would be an indication that moisture has gotten inside that probe, and when your process started up, the probe heated up and some of that moisture got driven off. The resistance of the probe goes up, so you're going to have a correspondingly higher temperature measurement. And typically that probe then is going to be reading accurately. However, it is an indication that there is a reason that moisture did get inside the probe and cause this problem. You may want to consider replacing it. You could also pull the probe out and throw it in an oven at a couple hundred degrees Fahrenheit and dry it out, and try it again and see if that problem comes back. Probably half the time it does, and the other half it may be okay. But if you want to err on the conservative side, I would just go ahead and replace the probe. When moisture gets inside the probe, it does cause shunting between the coils of the platinum coils or the lead wires. And this causes a low temperature reading. It causes the resistance, or the measured resistance, to drop, and a correspondingly low temperature measurement. It's real easy to check. We take a meg ohm meter, one probe to the leads on the probe, and the other one to the probe sheath. We should be about at least 100 meg ohms at room temperature, and this test is done at 50 volts DC, and these are minimum numbers. If you look at manufacturer specs, you're going to see that they do this test at 500 volts DC, and they want to see at least 500 meg ohms. Some will say 1,000 meg ohms. You're going to see all kinds of different numbers, but as a minimum, you'd want something like this. The reason for the higher, more stringent test is that as the probe sees higher temperatures, the ability of the materials in it to maintain that insulation resistance decreases. And so we like to start out with a real high number at room temperature so that we're ensured that the probe is still going to read accurately at the higher temperatures. The magnitude of the error can be calculated, and you can go through all this math and stuff, and kind of the bottom line is, so if you have an insulation resistance that's 1/10 of a meg ohm, so we're way below that 100 meg ohm limit, it's going to amount to about 1/4 of a degree C error that it's going to read lower than what it should. You know, for a lot of processes, that's not a big error. I know some of our pharmaceutical applications are going to say, yeah, that's a huge problem. So it kind of depends on where the probe is used and how it's used, but it is a potential error source. Some of the other things we run into is slow time response. I've had situations where a probe is put into a process and it works just fine for a while, and then all of a sudden it starts responding slower than what it should. And this can be an indication of where the potting material maybe was damaged and its thermal properties have changed, and it slowed down the time response of the sensor. The only way to fix that is to go ahead and replace it. And if you have a temperature probe connected to a transmitter or maybe a chart recorder or some other device where there's a delay setting in it, it could be that that delay setting was changed either intentionally or someone was messing around with it. Typically I see in transmitters you can set a measurement delay for like up to 60 seconds, and that may be something to look at to see if that will help speed up that temperature probe. Some of the other ways that we see the kind of, I guess it was our most common failure mode, was it's indicating a higher or lower temperature than what is expected. Now, RTDs will drift, and the amount of drift is going to depend on how they're used, the temperature cycling that they're going through. If they're run at a real high temperature, they're going to drift faster. If there's a lot of vibration or mechanical shock, maybe due to, could be water hammer, it could be just, you know, something else in the process that causes that. And if it's vibration or some kind of mechanical shock, the temperature typically is going to drift up. With the insulation resistance, it's going to drift down. Now, we can go ahead and you can put in a heavier duty sensor. If that doesn't do it, another solution might be to use a thermocouple instead. They're going to be a lot more resistant to the mechanical damage, a lot more so than an RTD. Now, to go ahead and verify that the RTD has been drifting, real simple test to do is just to check the ice bath resistance. And this is a real, can be a real accurate test. We just go ahead and make up an ice bath with some crushed ice made with distilled water or purified water. Contaminants in the ice are going to change that freezing point slightly, so that's why we use purified water. Have it crushed, put it in an insulated container, and then pour in just enough water to kind of fill in all the little gaps in between the chunks of ice, and poke the probes into it. And one thing you have to be cautious of is you don't want to use the probe to jam a hole into the ice. You'd want to use a you know, screwdriver or something other than one of your good probes to pound a hole in that ice, because that can go ahead and damage the probe even further. So I want to make sure that you make those holes with something other than the temperature probe. You want to put it in that ice bath and let it stabilize for, you know, a few minutes. Hook up the ohm meter and go ahead and see what that measurement is. And if you have a ohm meter with a 3 or a 4 wire input, that'll go ahead and compensate for that lead wire resistance. If you don't have one of those and you just have the 2 wire meter, you can do this manually. And what you would do is go ahead and measure the resistance between the 2 red leads that you see on these probes. These happen to be a 3 wire circuit. And then you take that measurement and you'd subtract that from what you measure between the white lead and just one of the reds. And that'll give you the resistance of just the sensing element. And that's what you're looking for. And that number should be right around 100 ohms, and it needs to be within what the original tolerance class was. And that's what the 2 standards define, this IEC and the ASTM standards. On this graph, it shows right at 0 degrees C. This is where the tightest tolerance is at. And we can look at those tolerances either on the graph, or we can look at a chart like this. And this will give you, these equations will give you the resistance or the tolerance in degrees C at any given temperature. So if we were looking at just 0 degrees C, this factor drops out because our temperature is 0. So this factor drops out. So if we're looking at want to meet this ASTM spec, we'd want to be 100 plus or minus 0.13 ohms at 0 degrees C. And that holds for these other classes of probes. So that's a real good, accurate, easy way to test the probe to see if it's working correctly, if it's been affected by vibration. And once again, I'm going to mention that before you do an ice bath test, you should do the insulation resistance test. If you have poor insulation resistance, there's a possibility you can get some non-repeatable measurements out of this ice bath test. So I don't know, Jeff, are there any questions that we should jump in and do right now, or should I just keep plowing ahead?
Yeah, nothing at this point, but I did want to remind everybody if you do have any questions on anything that Bill's gone over, go ahead and type them into the Q&A section, and we'll go ahead and get you an answer to those right away, so that you know, as the question comes up, we'll try to get you an answer. So if I don't see any right now, so why don't you just continue on, Bill?
Okay, so a couple other things to look at here. Occasionally you'll have a situation where a heater in a process is it's cycling up and down, and the temperature in the process is going up and down, and it just never really gets stabilized. And this is pretty typical of the probe not responding to the temperature fast enough, or in some cases it's responding too fast. A situation where it might be responding too fast might be in an environmental chamber where the door is being opened and closed and product is being put into the freezer and taken out. There you would want a probe that has a very slow response time so that it's not telling the cooling system to turn on and off every time you open the door. And there are solutions to both of those problems. The easiest way to slow down a probe is just to put some kind of an insulating material over it, and a real benign one is just some Teflon shrink tubing or PVC shrink tubing. That will slow down the response of that probe quite a bit. Another way to handle that is to set a time delay in your transmitter or chart recorder, controller, whatever it may be. Again, I mentioned that earlier, where a lot of transmitters have a feature in them, especially the smart ones, where you can set a measurement delay up to about 60 seconds. Now, if you have a situation where the probe isn't responding fast enough, that can be a little more difficult. There are versions of RTDs that are built with fast time response in mind. They're typically going to be a smaller diameter, maybe a little different sensing element. Sometimes the coil element is a better choice for a fast response, and sometimes a thin film can actually be the faster responding sensing element technology. So there are solutions for that. Now, one of the biggest error sources that I see, and it goes to this indicating or higher, lower temperature than what is expected, is with stem conduction. The probe is going to check out okay in a calibration bath, but you put it in service and it's going to be reading too high or too low, and it's a bit of a mystery. Most of the time, it's going to be due to stem conduction. There are some solutions to this. The easiest one is to increase the immersion length of the probe in the process. That will help minimize the stem conduction effect. There are some probes that are designed specifically to be very tip sensitive, so you can get by with a shorter immersion length. Another quick solution is to just insulate the exterior portion of the assembly. Now, this would include the piping about maybe 6 inches on each side of where the sensor is installed. If it's in a tank situation, you may want to put insulation around the connection head and the whatever extension is between the connection head on the probe and the piping or the tank. And if you do that, it should respond pretty quickly in a process that's heated, and you're standing in room temperature. That temperature would go up within probably a minute or two of when you applied that insulation. That's a real quick test to see if you have a stem conduction issue. And if it's a cooled process, the opposite will happen. So, and one of the other kind of least common problems with stem conduction might be that if it's a probe and thermal well application, the probe might be the wrong diameter for the well or vice versa there. It's just, and so you've got a poor fit up between the probe and the well. This can cause a measurement error because you've got ambient air kind of circulating within the thermal well, and it's going to have a bit of a cooling effect. Plus, air in there is a really poor conductor of heat from your process to the temperature probe. And we can look at the magnitude of some of these errors. So if we have a 1/4 inch probe in a thermal well, and this is where it's fit up correctly, you got a 1/4 inch probe and the bore diameter of the well is about 0.26. So it's put together correctly. If we look at the immersion length down here on the x-axis, we can see that we need about 5 inches of immersion so we overcome any of the stem conduction error source. And this is in a process that's running at 120 degrees C. Up here we have our 100 degrees C delta between the ambient condition and the process temperature. And the numbers here are fairly conservative. The data was adjusted to have a bit of a safety factor in here. So in some processes, you're not going to see anywhere near, like if you have for example, a 2.5 inch immersion thermal well. In some processes, that is going to work okay, and you're going to see much less stem conduction than what this graph would indicate. So just a little word of caution to anybody out there that's kind of panicked that has 2.5 inch immersion wells in a pipeline and they're going, oh my goodness, we've got a bad measurement. Not necessarily. A direct immersion probe, you can see we can get a more accurate measure with a shorter immersion. So here we're, maybe 3.5, 4 inches, and we're less than 1/10 of a degree of stem conduction error. And now the magnitude of the error decreases with a decrease in the delta between the ambient and the process. So if your process fluid is the same temperature as the ambient, you're going to have 0 stem conduction. That's kind of the ideal situation. But as that delta increases, you're going to see an increasing magnitude in the error. With a smaller diameter probe, we can see we get down, now we're maybe 2.5 inches here where we've got a fairly good temperature reading. So, some other sources of trouble. With 3-wire circuits, these kind of depend on each one of those lead wires having exactly the same resistance. And if we have a terminal block or a connector in line, and one of those terminals or a pin on a connector might be corroded, that can cause a measurement error. So we want to make sure that all of these connections are done and kept clean. Connectors are not worn out, for example. If we switch over to a 4-wire circuit, the way that the electronics compensate for the lead wire resistance, they'll actually take into account all the difference in resistance between each of those 4 leads, and will completely eliminate all that lead resistance and some poor maintenance on terminal blocks and connectors and things. So that's always a benefit of using a 4-wire circuit over a 3-wire. Some of the examples here, good clean tinned lead wires. Spade lugs can help if you frequently remove the probe and put it back into service. It helps prevent the lead wires from getting frayed where you may have some broken strands, bird cage, just a kind of a general mess. And then if you do use a connector, use a high quality connector with gold-plated pins. Terminal blocks should be made of a material that does not soak up moisture. As you can see in this photo here, did all the right stuff, had a good terminal block, the connections were clean and tight. Unfortunately, they had a piece of flex conduit connected to the connection head, and it was not an airtight conduit, and they had a lot of metal dust around. It eventually made its way inside the head, caused some shunting on the terminals here, and they were getting a low temperature reading. That one took a while to figure out, but after they switched over to a sealed conduit, everything worked fine. So with that, I don't know, Jeff, are there any other questions? I was going to jump into some thermocouple troubleshooting now.
Yeah, just a reminder, if you do have any questions, go ahead and type them into the Q&A section. Doesn't look like we've got any right now, but if some should come up, go ahead and type them in, and we'll get you an answer for that. Otherwise, I'd say continue on.
Boy, I didn't think I covered everything. Someone must have a question, right? So anyway, so thermocouples, another real common way of measuring temperature. They're very simple construction. So we have two metal lead wires. You connect them together, and they're kind of dissimilar metals. So if you connect them together and like put this junction inside of a heat source, and this is at ambient, you're going to get some kind of a voltage generated, and you can measure that voltage and have it correspond to a temperature. That's the same kind of basic construction. This happens to be kind of a insulators and wire type construction. And RTDs, thermocouples, can use the same type of mineral insulated cable. And if this were if these were thermocouple conductors, manufacturer just weld these things together here to make the junctions, put a little end cap on it, insulate it, and that's your thermocouple. They can also be done just with maybe a Teflon insulated thermocouple wires, and they're just shoved into a tube and sealed in place. So very simple construction. What could go wrong? Unfortunately, there is some stuff that can go wrong. In the tip section here, there's either the grounded junction or the isolated or ungrounded junctions. Grounded junctions are welded right into the tip of the probe. Ungrounded are insulated. You can see here this one has just a little extra ceramic powder stuffed around that element junction and an end cap welded in place. And this is done for a couple different reasons. Usually if you need a real fast response, the grounded junction tip is good. If you have a lot of electrical noise in your process, you may want to go with the ungrounded. Some controllers or transmitters require an ungrounded junction, or they have a setting for either grounded or ungrounded junctions. So with that, I think we're going to do another little poll here, and we'll see what kinds of failure modes you've had with thermocouples.
Exactly. So there should be a poll that popped up, and if you could take a couple seconds and kind of tell us what's going on with your thermocouples, that would be great. And we make sure that we get those items covered in the presentation. Okay, it looks like we've got a pretty good spread of different issues with the thermocouple. Some are similar to the RTDs, but we get a couple seconds left here in the poll, and so we'll go ahead and show you the results here. And so it looks like again, open circuit, maybe a little bit more popular, erratic output, and again corrosion. And for anybody who did indicate that other was an issue, if you want to go ahead and type in what your issue was in the Q&A section, we'll see if we can't maybe get a diagnosis for you.
Yeah. Okay. So I'm surprised that open circuit was as prevalent as it is. Usually it's some kind of corrosion or erratic output is what I see the most often. So anyway, let's just dive into this, and we'll start going through some of the symptoms and causes here. Again, erratic output, it can affect RTDs and thermocouples. Thermocouples are going to be a little more susceptible to this because we have such a low magnitude of signal that we're getting from them. You know, we're trying to measure a voltage, and it's millivolts, and that can be affected quite easily by either radio frequency or electromagnetic interference. Usually with thermocouples, I always recommend to use a shielded cable in pretty much all applications. And if you're trying to run the thermocouple extension wires from your process, you know, a long distance over to a control panel or something, that can open up some potential problems with an erratic output. And one of the big ways, most common ways to fix that is just to add a transmitter right at the measurement point. And then you've got this fairly robust 4 to 20 milliamp signal that you're running back to your control equipment. Sometimes even a shielded cable isn't going to be enough to completely eliminate that RFI EMI type interference if you're running that wire a long distance. And then an inaccurate measurement. Thermocouples are going to drift. If you use them at a high temperature, they're going to drift faster, and you're going to see that you know, depending on the temperature that they see, it's just a periodic replacement is going to be the only really way to address that issue. Some of the metal foundries and things where they're measuring like molten metals, or maybe it's a extrusion process where you're heating up a block of aluminum before it's going through some kind of a drawing process. You're going to be replacing thermocouples quite frequently just because that high temperature causes them to drift fairly quick. They get contaminated, and then their output changes. And that kind of goes to this short life. Corrosion and contamination. If the thermocouple is not protected with another metal sheath or ceramics of some kind, it can pick up contaminants from the process. It might be metals. It might be other elements like sulfur. Another real common failure mode there. And you can, if it's a direct immersion style sensor, you can switch that over and use a thermal well to help protect it. And the well might be metals, or it might be some sort of ceramic thermal well that may be required to further protect that thermocouple. We get to the open circuit, where you're just getting no signal from it. It could be that that junction is broken inside the probe. You may have a short or another broken wire somewhere, terminal block. It could be that the wires are just hooked up backwards, and we can go ahead and check the polarity of those wires. If we look at thermocouples, they'll have typically some color codes on them. Now, the red lead is always negative. If we look at any of the base type thermocouples, like type J, K, T, or E, they're going to have the red lead as the negative lead. Now, on a type R, some of the other high temperature thermocouples, it could be a type RS or a type B, as in Bravo. These will typically be put together this like this manufacturer's probe is. They just wrote right on the ceramic sheath here that it's a type R, and then they show a plus here, and I assume that means that this lead is plus. Little hard to tell, but they'll have them labeled in some method like that. With a type R, this is going to be a platinum lead, and then this will be a platinum rhodium alloy. Some of the thermocouples you'll notice, like on a type J, for example, the one lead wire is going to be highly magnetic because it's made of iron, and the other is going to be just slightly magnetic. So there's some ways to tell the differences there if the color coding is not available to look at. Now, we had a few people had experienced some corrosion with a type K thermocouple used at high temperature. We have what's called green rot, and really what it is, it's just some kind of selective corrosion of the conductors used inside the probe. This photo here shows a dual element thermocouple. So there were 4 leads inside this mineral insulated sheath. So this was one of the hot junctions, and this was the other one. And we just sawed the tip off, and you can see this corrosion around the wires and how the diameter has been, or the cross-section area has been decreased from that corrosion. You can see just barely down in this area where there's more of that kind of the green kind of rotted material. And this is caused by either too much or not enough oxygen that's getting to that probe sheath. And it happens at higher temperatures. One of the ways you can test this in a type K thermocouple is that the one of the wires will actually become magnetic. Either one of these wires are magnetic or very magnetic when they're just brand new, but you will notice that it does, one of them will become magnetic if this green rot is part of your problem. So, you know, how do you fix this? Well, it's a matter of getting the probe either isolated completely from any kind of oxygen. And if you go out on the internet and just Google green rot, you're going to get a whole bunch more information on this. And I kind of don't want to go into the rest of it here, but you'll get a lot of good information that way on how to prevent it. So one of the other reasons for kind of no signal actually poor accuracy out of the thermocouple, it's verify that your instrument that it's connected to is set for the right type thermocouple, and that it's has specified either grounded or ungrounded junction.
Okay. Bill, before we go too much further, we've got a few questions here, so maybe now's a good time to jump in. And so this was on some of the failure modes that folks had indicated as other, and so we got a little bit more information. One of the questions from Matt is he has a type K thermocouple, and the temperature drifts upwards and sits about 5 to 8 degrees F too high for about 15 minutes after power up, and that's at room temperature and air, and it's apparently just sitting on his desk. So he's wondering what might be the situation.
Oh, that's very curious. Well, let's see. I suppose there could be a few different reasons for that. I don't know if there might be some self-heating going on depending on, you know, what you have this connected to. I really can't think of any other reason other than that there's some issue with the meter that you might have it connected to. And unless it's, and I assume that you've got some other way of monitoring or knowing what the temperature is, and I know my desk is a lot colder than the room air temperature because it takes about a half a day for it to warm up after the building's been at the evening temperature. So I don't know if that could be part of that. So that's a bit of a mystery. I don't know if anybody else has any thoughts on that. Maybe you could just plug in a potential cause for that in the search or the chat or the Q&A box.
And we would be, happy, Matt, if you've, got some time, later on today or this week, if you'd like to give Bill a call or shoot him an email, we'll see if we can identify what might be going on there. Another question as well is are there different thermocouple types for reading solid surface temp versus air temp?
No, there's just a given number of thermocouple types. There's the base metal types, which is a type JK, T, E, and then there's a type N also. Yeah, any of those can be used, for either surface temperature or air temperature. There are some differences in accuracy between them. Like a type T will give you the most, has the capability of being the most accurate. And for air temperature, if it's like if you're just reading ambient temperature, an exposed junction thermocouple would probably give you the best response time and the most accurate measurement.
And then we've got another couple questions in regard to, again, some of the failure modes that they're seeing, significant inaccurate readings in a proven system from anticipated temperature, and then another one is drift from calibration data over time. So maybe you just want to talk a little bit about the standard drift and the reality of thermocouples.
Yeah, it's could be thermocouples or RTDs, and there is the I guess I classify them as, you've got the sensor errors and then you have the installation errors, and a lot of times the installation errors can be a lot larger than the temperature probe errors. So you can have a temperature probe calibrate fine in the bath, throw it in the process, and it's not going to read right. And it's because you've got some stem conduction or some other issues with how the probe is installed into the process. That would be the first thing that I would look at. And there it could be a simple test of just adding some insulation around the probe. And if it's in a piping system, for example, maybe a little insulation around the pipe on either side of where the measurement point is being taken, just to take that stem conduction potential cause out of the off the table. And then the other drift from calibration data over time. Yeah, both RTDs and thermocouples will drift, and it depends on the way they're used. Again, high temperatures, temperature cycling, vibration, shock, all those things are going to cause both technologies to drift over time. Thermocouples can get contaminated from the process when it's used at high temperatures, and that's going to cause them to drift even faster. So,
okay. I
don't know if there's anything else, Jeff,
yeah,
that we should cover?
We've got one more question here, and then we could move on. For some high-temp thermocouples, the calibration process itself may change the behavior of the thermocouple. How can you show metrology traceability for one-use thermocouples?
Oh, that's another good question. Typically, when the thermocouples are manufactured, the wire is tested for homogeneity, and that's when you really know what accuracy the thermocouple is going to have. if it's been used in the process, you're not going to really be able to go back and retest it. It almost has to be done by comparison with another good thermocouple or some other temperature measurement method. The one use makes me think that this might be in a situation where you've got molten metal that you're measuring, and they use just a thermocouple. It takes one reading, and then you have to throw it away because it has changed its calibration after that. Because they do get contaminated very quickly in those types of uses. But the best way to calibrate the thermocouple is to do it by comparison. So if you have it installed in a thermal well in a process, for example, you'd want to pull that thermocouple out, take a known either thermocouple standard if it's a real high temperature process, or you may want to use an RTD standard, stick it in the well and just do a comparison calibration to it. A lot of times it's just cheaper and simpler just to replace the thermocouple with a brand new one of known accuracy.
Okay, thanks, Bill.
So moving on to some of the other things here and finishing up the one way to test the rest of your system is to use a thermocouple simulator or calibrator, and that'll help determine if your thermocouple in the system is working correctly. Extension wires, we need to make sure that those are the same type as the thermocouple. You can't just use copper wire and connect it up to your thermocouple and expect a good measurement. It has to be either thermocouple grade wire or thermocouple extension grade wire. And if you have a short circuit somewhere along that line, it's actually going to create another junction, and then you're going to be reading an average between that junction and the one in your process. Could cause quite a large error. Again, RFI, EMI, use shielded cable, keep the runs as short as possible, or add a transmitter. That's probably the best way to eliminate any kind of RFI, EMI issues with thermocouples. Same slow time response issue exists with thermocouples as they do with RTDs. Typically, thermocouples are going to respond a lot faster than an RTD. So, if you have a process that is looking for a slow time response, that could cause some issues. And then once again, I mentioned earlier about the bore diameter of the thermal well matching the probe, and we like to see at most a 10,000th difference in the bore diameter and the probe diameter. And then heat transfer paste can also go a long ways towards correcting a poor fit up in a thermal well. It also helps with the time response. If you need it a little bit faster, adding that heat transfer paste in the well will help with that. And it can even help with stem conduction a little bit. And here you would need to make sure that when you put it in the well that it's only going down on the very tip, and it only covers about an inch, maybe an inch and a half of the temperature probe in the tip. You absolutely don't want it running all the way up inside here, because that's going to make your stem conduction and everything a little bit worse. It'll just nullify whatever you've tried to do down on the very tip of the thermal well. So, and with that, if we have any other questions, we can go through those now. And feel free to give me a call or shoot me an email if you've got some other little more involved questions that you'd like me to take a shot at. I don't know if we had anybody else take a shot at answering some of those other questions we had earlier. Jeff,
yep, I took a quick look. It doesn't look like right now we've got any other, any recommendations on or recommended manufacturers for heat transfer paste or even type of transfer paste?
You know, one of the real common ones is it's similar to the heat sink compound that's used on integrated circuit type stuff. It's just, I think it's zinc oxide and a silicone oil paste. It's got a good temperature rating. It's good to about 200 degrees C. There are some ceramic type materials where they're mixed with water into a paste. You put those down on the tip of the well, stick the probe in, and then the heat in your process drives off the water, and that ceramic material fills in that air gap and does a pretty good job that way. So those are a couple different types. I've had some cases where in a refrigerated process they use like a silicone oil in the well, or even propylene glycol or ethylene glycol, basically antifreeze. So any of those, just to take up that air gap, and if it's a good thermal conductor, they'll work pretty well.
Okay, unfortunately, it looks like our time is up, so we want to thank you for joining us. If we did not get to your question or you'd like to further discuss a temperature measurement problem or application, please go ahead and give us a call directly. Also, as a reminder, we will be sending a link to the recording within the next few days. It will be posted out on YouTube. And also, please join us for our next session in May, testing and documentation of RTDs, thermocouples, and thermowells. And with that, have a great day, and we hope to see you next time.